Hi, everyone, and welcome to the third day of the Machine Learning Using Galaxy webinar. My name is Fotis Psomopoulos. I am a researcher at the Institute of Applied Biosciences at the Center for Research Technology in Greece. And today we are going to go through classification activities and exercises using Galaxy. On Monday, we went through a broad overview of what machine learning is, and just as a quick reminder, these are basically the two main aspects of machine learning. We have the unsupervised learning, which includes clustering, for example, and we have supervised learning, which includes classification and regression. We've already seen regression quite a lot, and I am really happy to see that a lot of people actually went ahead yesterday and went through the exercises on their own pace and on their own time, and I hope you find it useful for your own work. Today we're going to see a bit more about classification in supervised learning. Just again to put it into a context, in supervised learning we have classification, and under classification you have several different algorithms that can help you do the task classification. I haven't yet touched upon what classification actually is, but this is what I will try to do as an introduction before we dive right into the demonstration itself. So these are some of the algorithms and the methods that are being used for classification purposes. We're going to see a couple of them today, but most of them are quite extensively used, and you will see them in one capacity or another. So going directly into the classification and supervised learning workflow by itself. So basically it consists of two parts. So the main purpose is to somehow identify an instance, a record, a data point, which class it's assigned to, which label it might have, given a specific set of labels. In the figure you see here, we have basically two labels, two classes, class 1 and class 2. And the classification is essentially identifying which is this black line here that can help us separate between these two classes. And in order to do that, most of the algorithms in classification require a step called training. In the training step, what you take is the raw data that you use to train your model, to create your model. And for those particular data points, you actually need to know the labels. So this is the reason why we call this the supervised learning process, because you already know the outcome. And you can go through a feature extraction phase, and we will be talking later today about feature selection. And by establishing what are your key features, you try to create a model. So the algorithms themselves, what they do, they produce this model part. As soon as you have the model, you can try to evaluate how well you've classified your already known instances by comparing against the labels. And you can do multiple iterations of this process. So if your evaluation is not good enough, you go back to the feature process maybe, or even the training if your features are good enough. You retrain your model by changing some parameters or changing some other aspect of the process. You create another model, and you do this process again and again until you are happy enough with your evaluation. So as soon as you have your model, you can actually use this to do prediction. And this is the ultimate goal of your effort. So if you know this black line, if a new circle, a new data point comes in, you can check in this two-dimensional space of the figure which part of the line falls in. It's the blue one or the purple one. So you have a new data, you apply the exact same feature extraction process, so you create the exact same feature vector that the model understands. You apply the model and you predict what the label of this new data is. So this is roughly how the supervised learning process works. So essentially what we are discussing is that supervised learning and classification specifically is to apply what has been learned in the past by using the label examples in order to predict the future events. In most cases, you start with a known training data set, and your model can be used as a prediction for any new input. So a key aspect to remember here is that the evaluation essentially tries to compare the output of the model that is produced with a correct intended input. And if there are errors or if there is not good enough evaluation, you try to improve this prediction model accordingly. So going specifically into the classification, there are two major steps, as you can probably infer from the previous figure as well. So the first is to actually build the classifier. The classifier itself has the learning step, in which process the classification algorithm that you selected actually builds the classifier. Based on the training set that you provide in this phase, you try to extract what could be the class from this model and try to see whether you can match this against each other. As soon as you have this classifier in place, this model in place, you can apply it in a test data set and see whether the classification model, the classification rules you've created, actually estimate the correct labels, and if so, what is the accuracy? How well it predicts those values. There is a usual question at this point. So classification and regression both fall under the supervised learning process. So there is a question: what is the actual difference between a classification process and a regression process? I borrowed this this very nice image from a link you see on the slides. So essentially, classification tries to create this black line which separates the red from the blue in this instance on the left-hand side. In the regression case, you try to estimate how you can recreate your actual points. In other words, what would be the appropriate function that would, if provided with the correct parameters, could produce the data points that you have provided as input. I'll try to explain this a bit better using this sort of table. So, and this is in very broad terms, so take it with a grain of salt. So in classification, what you're trying is that you have both discrete and categorical values, and you try to estimate to differentiate your data points across these particular values. In regression, you actually can you have as a goal to calculate an actual number, a real number. It could be, of course, a discrete or a categorical one, but regression actually works best when you're talking about continuous values. In both cases, we are talking about supervised classification problem, because in both cases you try to predict a particular value. However, in the classification case, what you're trying to do is to assign the output of the model to a particular label, to a class. So red and blue in the previous instance. So in this case, in the left-hand side, the classifier is going to give me a red or a blue. That's the outcome. In the regression case, again, supervised classification problem, the end goal is to predict a natural value. So given again the data point, the parameters, the different variables of this data point, how can I predict what the actual value of your output might be? Or in other words, if you look at the right-hand side, if I have, for example, the gene 1 value and the survived years value, so the X and Y values, how can I predict exactly where it's going to be located? So provide the coordinates in this two-dimensional space. The final point is mostly in terms of views. So in classification, you try to predict a type, because a type can be connected to a label. You have type 1 or type 2, harmful versus not harmful, for example. In regression, you try to actually predict a value, which is a real number. In a wider context, it could be to predict the house price. In talking more in life sciences, you're trying to predict the survival time of a patient. So going back in this left-hand side, having the value of gene 1, and the regression model, you provide a value for gene 1 in the regression model and gives you what the survived years might be. So I hope that I clarified that a bit. I'm going back to the linear regression you've already seen, just to provide a context. So the regression can be used when you're trying to calculate some continuous value. So can't compute that. So when you actually want to predict a future value of a process, of a mechanism, this is where a regression algorithm, whatever type of regression algorithm, can be actually used. If you look at a two-dimensional set of observations, so you actually have two variables, continuous ideally, linear regression tries to find, essentially to the best of its ability, what would be the line that would connect all these data points, or at least have the maximum overlap with that. So in this case, the actual line that is going to produce the model itself is one way for us to describe what is the underlying mechanism that can describe the data set. Again, I'm going to go back to this image. If that was an actual problem, I would say that the x-axis was the expression of gene 1. I would say that the higher the expression of gene 1, the more years the survival outcome might be. So the line itself, which is a linear direction that goes through all these points, gives me some insights on what is the underlying mechanism. So why this happens, this is called the discussion. But the model itself helps us sort of uncover that this is a trend that exists. Also, if you have an appropriate regression line, you can use it as a prediction. So if I can have another gene in the future and a new value for this next expression, I can find what could be the survival years for this particular instance. There are some issues, of course. So linear regressions work quite well, but if there are features that you have connections to each other, are correlated, you have multicollinearities, or you don't have even linear connection between them, it might not give a good enough approach. So this is just to provide a connection to what was said on Monday. Going forward to classification, another quite often used structure or algorithms are the decision trees. So decision trees can be viewed as a series of questions. So starting with a variable 1, ask, does variable 1 has a value greater than x? If so, what's the next question? So in other words, think of it as a continuous set of questions in the form of a tree that you can continuously ask and eventually lead to a decision. So they are very rarely used as single trees, but quite often they're used as combinations. So random forest, which we'll be seeing as the demonstration afterwards, is one example. Graded tubular is another. And they are quite easy to use feature interactions in the sense that I can have a set of questions about different features one after the other and sort of connect them in that way. And of course, they're non-parametric, so I don't have a parameter there. I don't really need, in that case, to think about outliers or if they are linear or non-linear in my underlying data. There are some key disadvantages, though. So the first one is that it's quite often that the tree needs to be retrained, rebuilt, when you have new data points coming in. And this means that if it takes time to produce this, it is some time that you need to spend retraining your model with every new data points. Also, decision trees, the single decision trees, can easily overfit because you can have very specific questions in the form of if gene expression is over 0.01657, then it's tumor 1. If it's below 0.00165, it's tumor 2, which is very, very specific to a problem that I've used to create the decision tree itself. So it might not work using a different data point. However, Other methods that are relying on decision trees, like the random forest or the bushes trees, actually resolve this kind of problem for the overfitting. And the final point is that having a lot of features can lead easily to a lot of memory required to actually train this, because you're going to have, the more features you have, the more questions you're probably going to have in order to split the different branches of the tree. So trees are usually quite well to help choose between different courses of action, because they are easily interpretable in that sense, but they do have these downsides. So moving from the decision trees to the random forest. So the random forest is essentially a set of decision trees, multiple decision trees. And it can be applied both to regression and classification problems in general, and can be applied with large data sets. And the key advantage that they have is that they can help identify the most prominent features of the data. And we're going to discuss a bit more about feature selection after the demonstration. It is highly scalable, so it's quite extensively used in different different data sets, and it sort of works okay in terms of performance. So it's not too fast, not too slow. The downside is that you might need to have multiple iterations in order to produce a good enough model, and in that case, having this in mind could be a good practice. I'll move to another classification algorithm, which you're also going to be seeing later, called support vector machines. So support vector machines are a quite extensively used method, especially if you're talking about recognition. And it's ideally suited when your data has exactly two classes, which means that a lot of the cases in SVM are in support vector machines are designed so that you lead to two classes. The key advantage is that it leads to very well trained models. So the accuracy of the models is quite high, even if you have not linear data. So you have quite complex data or complex structures in it. The downside, and it's a key downside on several occasions, is that first of all, it's memory intensive, so you require a lot of memory to actually train this properly. And what is produced as a model, it's hard to interpret. It's not as easy to transform into a decision tree type. So you can ask questions whether this feature has this value or not value. And it's also a bit tough to tune it, to find the correct parameters in order to ensure that it's not overfit, it's the best connection, and so forth. It's extremely popular in text classification, and you have high dimensionality, but it's also quite used in bioinformatics applications, especially you have a large number of numeric features. The last point I want to highlight before we go to the demonstration is, okay, we have some algorithms, whatever we are going to be looking, how can we test it? How can we validate that? As I said in the beginning, classification works by testing against a known set of labels. So based on what you have in the beginning as the known labels, you can evaluate whether it's going to be a good enough accuracy of the model. And the good practice is to actually have a second data set, the test set, which is not used during the training phase, that you can use this to test again. But if you look at the actual values that are going to be used in order to evaluate how good this accuracy is, we have basically these different, mostly these different parameters. So the first one, and I'm going to go through them because we're going to be seeing them later on, is the confusion matrix. The confusion matrix is what you see here as the image, where you have essentially for the true labels, actual, no, actual, yes, in this case, and the predicted labels, the ones that the model produces, and how well these have been identified. So from the actual no cases, 50 of them were actually predicted as no, but there were 10 that were mislabeled as yes. And from the yes labeled, 100 out of the yes labels were predicted as yes, so they were correctly assigned, and only 5 of them were misclassified as no. So by having this table in mind, essentially you want high values on the main diagonal and very low, ideally 0 values on the off-diagonal cells. So this is the confusion matrix. Usually you see it as a image figure with colors, so that you can quickly see the actual difference in numbers. There are also some very specific values that you can use, which are called precision, specificity, and sensitivity, which are defined as ratios between the true positives and sums of true positives with false positives with true negatives, and true positives with false negatives, respectively. These values can be used to identify how well or how accurate your model is, and they are always calculated during the evaluation process of the model place, but they are also quite extensively used in the figure that you can see on the bottom right part, which is called the ROC curve, receiver operating characteristic curve, and the area under the curves. So ROC and AUC curves. So what they do is essentially the ROC curve is the orange line that you see on the figure. There are 3 boundary cases. There are 2 boundary cases. The one boundary is that the model is really, really bad. And in that case, the orange line is going to be exactly on top of the blue dust line. In this case, it means that your 2 classes, or however many classes you have, are essentially indistinguishable to each other. And I want to draw your attention on the 3 plots on the top. The plot on the top right, where you see that the green dots and the blue dots are basically exactly the same. This is the case where the 2 classes are actually indistinguishable. They are the exact same distribution, but different color. The best case scenario is where the orange line actually goes sharply to 0.01 and then straight ahead. So it's basically following the top part of the box. In this case, this is the ideal case of the classifier. And going back to the 3 figures I have on top, it corresponds to the top left side of the plots, where you see that the green dots and the blue dots are actually quite easily separable. There is no overlap in their distributions. The usual case is the one that is actually listed in the figure, where there is some overlap between the two class distributions. So in the middle plot on the top, so you see that the green dots and the blue dots have some overlap. This is the red line that is drawn here, and this is why you have some false positives and some false negatives. So this is basically a short intro to the classification and algorithms and how they're evaluated. And what I'm going to do now, I'm going to stop the presentation mode somehow. Yes, I think I managed to do that. And I'll go directly to Galaxy so that we can start working on an actual problem. So what we're going to do, we're going to use the exact same process as on Monday. And the first thing I'm going to do is actually create a new history. So I clicked on the plus sign right here, and you see now I have an unnamed history. I'm going to rename that as classification, in Galaxy. You can use whatever name you. Oops, sorry. That is, I did not place enter, so I just clicked and I lost what I've typed, classification in Galaxy, and now enter. Yes, perfect. So what I've actually done now, I've created an empty history. So my next step is to go ahead and load some data. What we're going to be using are data from a biodegradation problem, and experimental data from the Japanese Ministry of International Trade and Industry. They are chemical data, and they will provide essentially information, different chemical features that can predict whether a particular molecule is biodegradable or not. So the first thing to do is actually load up the data. So we have two data sets, and I actually need to give me a sec because I need to copy this from the URL. So there we go. The first thing I need to do is to load the data from the URL. So what I'm going to do, I'm going to select these links. I'm going to copy them from here. I'm going back here, and I'm going to use this icon to upload, download from URL link. I'm going to paste from fetch data. I'm going to paste the links selected here. So essentially, let me start this, and I will discuss what's happening. Essentially, we have two files. The one is the train dataset. It's called train rows, and it contains 837 molecules. So this is the one file that we're downloading. And there's another file that is called test rows, which is the test dataset. And we're going to be using this in the testing phase of the classification problem in order to evaluate whether our classifier, our model, is accurate enough. There is an extra file called test rows labels, which actually contains the labels of the test rows of the test dataset in order for us to validate whether it's working or not. So I see that it's already done. So let me close this window. As you can see, because I've downloaded from the from URLs, the actual names of the jobs here are the full URL. So the first thing I'm going to do, I'm going to edit the attributes, so it's going to be more easy for me to remember what this is all about. And I'm going to name this train rows. That's done. I'm going to edit the attributes. It's the icon here, and I'm going to rename this to test rows. And the same with the test file here. Again, edit attributes and test rows. Excellent. So now everyone should be able to have this in mind. So we can also see how the data looks like by clicking the icon, and I've just clicked for the train rows. You should be able to see something similar to that, and you can see that there are a lot of features here. All of these are chemical features that I cannot claim that I know a lot about, or if anything at all, to be honest. But the important part is that the last column is called class, which actually is values between 1 and 0, whether our model can be, our molecule, our corresponding molecule is biodegradable or not. So you can see here some zeros. There were also some ones in the top. So the first step is to start with a linear model. Let's try to do a regression classifier. In order to do that, I'm going to go down here to the machine learning box, and I'm going to select the generalized linear models tool that will allow me to create a logistic regression classifier. So an important point to say here is that I'm not going to use linear regression classifier, but rather logistic regression, in the sense that I'm aiming to not predict the value of the class. It's going to be 0 or 1. So I'm not going to expect a value of 0.5, for example, or 0.7. It's either 0 and 1. So although it's a number, I actually need to predict a label, an actual non-categorical value. So in that case, I'm going to select a logistic regression. So the first thing is to select what kind of classification task I want to do. And there are two options here. One is to train a model, and one is to load a model and predict. And what I want to do now is to actually train a model. So that's the first step. The second step is to select what type of linear model I want to create. There are a lot of options here. What I want to do is to do a logistic regression. I also would like to mention that there is this logistic regression with cross-validation, which is a good enough plan to have in mind, especially if you want to retest your to ensure that you increase your accuracy bit. But I'm not going to go into this process right now. So as input data, we have tabular data. We actually specify, we reviewed that, and we are certain. And the second question is, okay, we have selected the model. We know what type of input we want, we expect. What is going to be our training data set? We have essentially we have two different data sets, the train and test, and because we're training, we're going to select the train rows. As we saw earlier, the train rows actually does contain headers, so I'm going to select yes here. But it's also important to select not everything. If you recall, the training rows, the rows themselves, the data itself, at the end contained the actual class. And I don't want the feature class to be used to train the model for the very simple reason that if I use the class feature as the training process, it's going to be the only feature to be used, because the feature class can always predict the class. It's the same thing. So the first thing I need to do, so not the first, the thing I need to do here is to actually exclude some options. And as you can see here, I can select columns. I can select all columns excluding some by index. I can select columns by specifying the header names, and I can select all columns excluding some by header names. I'm going to go directly here, and I'm going to type class. Right. Sorry, let's do it like that first. So we have defined how to train. So the second question is, okay, we're going to train with this data set. So we selected essentially all columns, all features of the trained data set, with the exception of the last column, which is our class. So in the question, what is the data set that's going to containing the class labels? Essentially, it's the exact same one, which is train. It does contain headers, we've seen that. And now we actually want to select a single column. So here I'm going to select a column by specifying the header name, and I'm going to type again class. So these are the main parameters. Going to get through them quick fast. I select the classification task. I'm going to train the model. I select the linear model, which is the logistic regression in this instance. We have tabular data located in the train rows file we've loaded before. I want to exclude the class feature because this is not going to be used to train the model. And in order to identify what are the corresponding class labels, I use the exact same file, the data rows, but now I specifically include only the last column, which is the class. And with that, I can press execute. It will take a few seconds to run. And the question here is, I'm actually going to select it again to discuss something while it is running. Generalizing the model, excellent. So it is important to see that there are also some extra advanced options that you can see here. I will go directly to select the logistic regression so we can see the advanced options for that. And you can see that there are some particular options here that can be used to refine the process of the generalized linear model logistic regression process. We haven't gone through this in this case because, generally speaking, you should either automatically find a way to optimize that by doing, for example, a hyperparameter selection process, or you actually know what you're running before you start changing them. So you might need to have a better understanding of what the impact of these parameters are before you run the process. So I see that it's still in the queuing process. Let me see. So while it's waiting, I can start defining what the next task might be. So, okay, now it's actually you can see that it had started executing from my end. So as soon as this is done, the next step for me would be to actually evaluate the model, right? I have created the model itself. It has some aspects, but I don't know the model itself. But the next step would actually use to evaluate the performance of the model that we created using the test dataset. So in order to do that, we go to the exact same tool, which is the generalized linear models for classification and regression. And we're going to select another task. The task we're going to be using now is, instead of a training model, we're going to load the model and predict. In this case, what we're going to be using is the output of this particular tool as soon as it's done. And the data that we're going to be using in order to do the evaluation is going to be the test rows. Okay, actually it's done. So that was fast. So what I want to do first is I'm going to go to the output of the generalized model. I'm going to change the name, and I'll change it to logistic regression underscore model, so that I have clearly listed here what are the models that I have. Now that this is done, I will go back to generalized models, and I'm going to do the prediction. So as I said, I'm going to do the load model. As you can see, it's clever enough to understand that this is the correct model that it can take. So even if I had multiple models, it will still select the appropriate one. And I'm going to select the test rows. And as you recall, the dataset does contain a header. So I put yes. And what I need to do is to predict the class labels and then execute. So it's already being sent. And as soon as it's done, the next question is, all right, we're going to be seeing that, how we can actually visualize this information. If you recall from the presentation earlier, we need some specific aspects, some specific information to be listed. I'm going to switch to the presentation just to see the slide. We're talking about, we want to see the confusion matrix. We want to see some metrics regarding precision, specificity, recall, and ideally, we also want to see the ROC and AUC curves. So in order to do that, if we see the output of the model, so first of all, the model of the logistic regression, if I click on the view, it will give me the option of downloading the model as a zip file. You probably do not see it. If I click on the view, it's going to have a pop-up saying, do you want to download the zip file? In the case of the prediction, as soon as it's done, we will try to see what the actual output might be in this case. But in the meantime, while this is done, we will need to do some extra steps before we do the visualization. So we have the information of the model as soon as it's done, but what we need to do is to somehow make compatible the test row labels with the output of the generalized linear model. So in order to do that, we need to slightly update and change the file calls test row labels. And the reason is that the output of the testing process will not have a header. And if we have a header here, it's going to be a bit confusing. So in order to do that, I'm going to go to the test. Actually, I'm going to test text manipulation. Here it is. And you select the process called remove beginning. It's going to be faster, I think, if I type this as remove beginning. Text remove. There we go. So if you go to the text manipulation, or if you type remove beginning, it's going to give you the correct. Wait. I probably typed something wrong. So it sort of refreshed wrong. Let me go back to the remove part, text manipulation. Come on. Sorry, my network today is not in the best of its capacity. Okay, text manipulation again. Apologies for that. Scrolling down a bit more. Remove beginning of a file. So I'm going to select this one. And what I'm going to do is I want to remove the first one line. Essentially, I want to remove the header of the file called test row labels. So this is not something that you always want to do. Is essentially you do this for this particular case in order to ensure compatibility with the output of the generalized linear model evaluation. So I'm going to run this as well. So it's going to be put in the queue here. So this job is actually running. So I'm going to give it a second or more. It should be done in a second. As you can see, the remove beginning actually has run because it was a fairly fast process. And I clicked on the icon of the remove beginning. So you can see that now there are no headers. If you click on the test row labels, you see that it actually does contain the header names. So the only thing we're waiting now is for that. In the meantime, I can start preparing how to visualize that. So again, what we want to do is to visualize different metrics of how well the classifier was evaluated on the test dataset, and we're going to use another tool here called, I'm actually going to type confusion because it always gives me the correct one. It's under the graph display data section, and it's a tool called plot confusion matrix precision recall and rock ACUC curves, which is exactly what we want to do now. So I'm going to click on that. And now what we need to do is to specify what we want to use to plot. So in order to use the input, right, this is not very informative. So the output of the remove the beginning was not a very informative name. So I'm going to go, sorry, I'm going a bit back and forth here. I'm going to edit the attributes of the output of this job to remind me what it actually is. So it's basically the test rows labels no header. I'm going to save that. And now it's going to be much more easy for me to remember. Excellent. All right, so I'm going back to the tool here, plot confusion matrix. So what's going to be the input data? The input data, what we're going to use to evaluate is the test rows with no header output that's prepared. The predicted data file is the one is being produced right now. It's the output of 5. And the model itself is the one that is listed here. It's a logistic regression model. So I'm going to wait a bit because I want to rename also the output of this one. Or alternatively, because it might be possible that it's going to be more efficient to actually take this from a previous history, I'm going to open my histories and I'm going to pick up, okay, there we go. I'm going to select this output and put it here. Good. So I'm going back to the process, and at some point it's going to finish, but I can move forward. So the output of, okay, that was good timing, I guess. Right, it just finished. I'm actually going to delete the one that I just put in. I'm going to do edit attributes here. So I'm going to rename this as the logistic regression results. Good. Save. There we go. Okay, so going back to the confusion matrix. There we go. I'm going to select correct tables with no header. Data finds the result. So I'm selecting this one and the model itself of the result. I'm going to execute. So now you can see this particular job produced 3 different outputs. And the one's going to be the confusion matrix. We're going to visualize that. The other one's going to be the precision recall and F-score of the output. And finally, it's going to be the ROC and the AUC curves. So as soon as this is done, we're going to view them and see how well our model has been run. So essentially, if you recall, let me go back here. The confusion matrix going to we will expect our values to be mostly on the main diagonal, and off diagonal it should be very low. And in terms of the precision recall and F-score, we want to have essentially values as close to the 1, to be honest. We want the false positives and the false negatives to be closer to 0. So let's go back here. Okay, excellent timing. They've just finished. So I can click on View Data. If I click on that, it's going to be shown in the main Galaxy window the output of the confusion matrix. But alternatively, I can right-click and open the new tab, which helps me because it's much more clear what's happening. So as you can see, you see that true class labels are here, so 0 and 1, and the pre-class labels are here, 0 and 1. And as you can see, we have 0 and 0, they are high, 1 and 1, they're high, so you have about 500 correctly allocated as 0 and very few allocated as 1s, and you have very few 1s allocated as 0s, and a lot of 1s allocated as 1s. So the difference with the image I've been using here is that it's actually the rows have been swapped. So sorry, going back and forth now. So instead of being on the main diagonal, it's actually off the diagonal. But if you look at the labels, you should be able to identify what the correct values should be. So all in all, it's a decent enough representation. But let's check the other metrics as well. So I'm going to do the same thing with the precision recall and F-score. So it's loading now the image, and as you can see, all those values are fairly okay. They are like 90% here, recall, F-score, and precision, and on the other end, it's down here. Let's have a look at the AUC curves. And okay, as you can see now, the actual ROC curve is not bad. Ideally, we want this to be as steep as possible, so from 0 to 1 directly, and then from 1 to 1 another line. But the actual values are not really bad. You see that the red line, the by chance, is right here as an indicator. And the AUC, the area under the curve, so how much area you have under the curve, is close to 1. Ideally, we want this to be equal to 1. So all in all, it was a decent enough classifier, but we know that we can do much better than that. So this was a logistic regression classifier. I'm going to move to the next one, which is the KNN, the K nearest neighbor classifier. So the K nearest neighbor classifier essentially works as follows. Every sample looks at K of its nearest neighbors. So of the K other samples that are located near to itself. And it's classified by the majority of its neighbors. So if I have a sample with 5 neighbors and these 5 neighbors, and 4 of the 5 neighbors are class 1, my sample will also be classified as class 1. So it's a majority vote. And K is essentially how many neighbors I'm going to take into consideration when doing that. K is always, of course, a positive integer value because I cannot have 1.5 neighbors. I have 1 to n neighbors. And at the same time, if I have K equals to 1, it means that essentially I classify my samples based on the class of my nearest neighbor. So generally speaking, KNN is a okay approach. It works unexpectedly well most of the times. So let's have a look at how this works here. So I'm going again go to the machine learning section. It's down here, if I recall, yes. And now I'm going to select the nearest neighbors classifier here. I'm going to, in order to save some time, I'm going to fill in the parameters, and then I'm going to discuss with them as soon as I run. So I'm going to train a model, nearest neighbor, it's tabular data. I'm using the train rows. It does contain headers. I'm going to select anything except the class. And then the dataset to use star is again the same one. It does contain headers, and I want to select by using the class. And I'm going to execute, and now I'm going to explain what I actually did. Right. So I'm opening this again. So again, I'm going to select a classification task. The first task, if you remember, the classification is 2 steps. The first step is to train the model. The second step is to predict, to load the model. So I'm going to train the model first. I have 2 different classifier types for the K nearest to the nearest neighbors. And the centroid is, instead of looking at the neighbors, you actually look at what is the approximation of them if you're looking at nondescript cases, but I'm not going to go into that now. So we select the nearest neighbors. I'm going to use the same data as before. So we're talking about tabular data. And in terms of samples, I'm going to select the same file, so the train dataset. There we go. So that's interesting. It started running and then it sort of stopped. Interesting. So we know it contains headers. So I click yes here. And in order to select the data, again, we want to exclude the class. We don't want to take into consideration features that include the class. So I'm going to I selected all columns, excluding some by column, by header names, and I typed class here. How to select the classes? Here I'm going to select again the same file, train rows. Of course, it does contain headers, the same file. And now I want to select only the column with the class. So select column by header names, and again, I'm going to type class. And then I executed that. A question that may come up here is that, okay, you talked about K nearest neighbors, where is K? There was no K involved in any of these parameters. So actually, if you go down to the advanced options, there is actually the number of neighbors that can be used, which is by default 5. So you can change this value, of course, based on your problem, on your data, and how you want to use this. For the time being, I went to the default value of 5 in order to show how this works. So this takes a bit more again. I hope this is done soon enough, and then I'm going to, otherwise I'm going to load one from the history again in order to proceed. So while I wait, I hope that you can imagine what the next step might be. So we have the nearest neighbors, and this is how we train the model. And as soon as we have the model, the next thing we need to do is to actually use this to predict. So it's going to be the exact same process. We select the nearest neighbors classifier, But instead of training the model, we're going to load the model. Here, we are going to select the nearest neighbor's output that's going to be produced here. As you can see, I can actually select the logistic regression model. I haven't tried that, but I assume that's going to fail miserably because it's going to be using a model that's not prepared for, because this is defined for the nearest neighbors classifier. So we select the correct model, and then we select the correct data. In this instance, we don't need to have the ones with the no header, because this particular argument actually maintains the header, so I can select the test rows as the input. We do contain headers, so we're going to use this to predict the class labels. So as soon as this is done, I can run the execute part, and we can visualize again how well it was produced. Okay, this is still running. In the meantime, let me see if there are any questions or any people that have raised hands or something along those lines, to see if I can address a particular point.
Hi, Fotis. It's Chris speaking. Yes. Yeah, so we do have a couple of questions. So we've Bjorn and his colleagues have been trying to answer them in writing, but maybe you can address them as well. So I will read them out and one by one, and then maybe you can spend some time answering them.
Yes, that is actually a good plan.
Yeah. So the first one is from Ramesh. Is there any possibility that a few of the, so that comes for the beginning of your presentation. So is there any possibility that a few of the healthy or two more falls into the other group, let's say by chance? So that's about the classification at the very beginning of your talk.
Right. So that is an excellent question, and the short answer is yes. It actually happens quite often, and this is the classification error that we are trying to address. So it's why we put all those metrics to evaluate how well it's going to be done. The confusion matrix that I showed here, yes, it's basically this case where we have some cases in the tumor, let's say case, in the no case, that are classified as healthy, yes case, and the other way around. So ideally, you want a classifier to be as robust as possible. So we want to ensure that there is minimum error, minimum cases of false positive or false negative in this case that are included. So yes, that was an excellent question. Let me see how this is running. Okay, still executing.
Yeah, so we have a couple of more. So maybe I'll just continue. There is another one from Janet. How do you know if the data is linearly separable, and especially when there is more than two dimensions, so you cannot easily plot them in a scatter plot?
All right, so that is a very good point. So generally speaking, we have different ways of doing that, and this is more of the feature selection and the feature feature selection process. So you can try to apply these sort of methods, and I'm hoping that we'll talk about them a bit later, of how you can test your features of any underlying structure. And structure in this case is whether they are connected to each other, or if they are features that can be used together to provide another predictor, another feature in this case. That being said, I'm not sure that there is a universal way or even a single way of identifying whether there is linearities or if your data is linearly separable or not. In most cases, in a real world scenario, it's in my experience at least, it may not be the best answer here, is that they have some non-linearities involved. The question I usually try to answer is how much those non-linearities have an impact into how the classifier is produced. So to answer in short, I don't know if my data is observable. I try to do different feature selection and feature transformation processes, hoping that I can find a particular set of features that and the corresponding classifier that actually leads me to a meaningful classifier eventually. So I hope I've answered this question.
So, do we still have time for this, or do you want to get on with
well, I would get one more answer, and then I'm going to continue on with the rest of the algorithms.
Okay, so there is one that's touching on the different ways you can evaluate the model. So why do we? So this is from Ramesh. Why do we need a precision recall and F1 score? And can you explain a bit about the interpretation of the results?
Right. Yes, that is an excellent question. So I'm going back directly here. So essentially, precision gives us an indication of how many of a class have not been correctly assigned. So in other words, you want precision, which is defined as the ratio here, to be closer or even ideally 1, which means that the number of cases that have been correctly assigned to their corresponding classes is actually exactly the same as the true number. False positives, the FP here, stand for cases that have been assigned to a class wrongly. So by having a large number of false positives, you actually have a lower number of precision. So in other words, precision is how well can you trust that the produced class, the predicted class, is the correct one. So the specificity is essentially the opposite of that. So the true negatives are essentially the ones that have not been classified as one. So in other words, if it has not been classified as class 1, how sure we are that it's indeed not class 1. So there is a connection between them, as you can see, but it's not that they are they are not one minus the other or something like that. The connection is how I can trust that what I predicted is correct, and what it's not predicted is also correct. The sensitivity is essentially a mixture of those two, and it's essentially the rate of which the ones that have been not classified. Let me try it in a different way. So if I know that I have 100 cases of class 1, and if my number is lower than that, if the number of cases that I actually get is 110, it means that I have a few that have not been assigned to this one. So you decrease this value. In all those cases, you want these numbers to be closer to 1 to actually ensure that you don't have any false cases. The false is the key aspect here. So that's why you want all those numbers to be directly as close to 1 as possible. So I hope I've answered this question as well, and this is still running. So I may have done this, so I know what may be the root problem for that. So I'm going to comment on this. If you recall, and I'm going back to the classifier like this. So if you recall, when I create the training model, I select the classifier, the correct one, yes, excluding by column header names, and then I type class. So the problem, and I did this sort of intentionally because I want to show you another aspect of Galaxy, is that I mistyped the name. So the header itself, it's not with small letter K, it's with capital K, which means that right now, Galaxy, I think, it's trying to figure out what to do with the wrong number. It's going to eventually fail. And if it fails, it's going to have an extra button here to debug. So what I'm going to do now, I'm going to load from my history the actual output of the nearest neighbor. I'm going to continue, and assume this fails, I'm going to show you how you can deal with similar errors, and also how can you report this kind of errors to the Galaxy team. And I have to say that they are very, very fast to respond. So this is the nearest neighbors model. So I'm going to grab this into my history, going back to my history now. Right, so now this is still running. Excellent. I do have the model. So now I'm going to use the same process. I'm going down back to machine learning. Where it is, here we go. Machine learning, nearest neighbors, and now I'm going to use this to predict. So I'm going to use the nearest neighbor model. I'm going to select the test rows. It does have a header, and I want to predict the class label. I'm going to execute. So hopefully this will run a bit faster. And all right, there are a lot of people actually running things now. Good. As soon as this is done, the other thing we're going to do is to actually produce again the same visualization aspect. So I'm going to type confusion again here in the tools. Plot confusion matrix, and okay, it's already running, which is good. And I'm going to select as input the test from labels, because we want to test against the labels themselves. The nearest neighbor result is going to be the output of this one, and I'm going to use the model to actually use those to test. So I need to wait for this to be done, and we're going to visualize the output again. All right, so while this is running, hopefully this will run much faster. So let me see if there are any questions still.
So we have one.
Yes. Okay, please.
So this is from Franco. Can you get the values of specificity and recall from the module?
Aha, this is an excellent question. I honestly don't know. I assume, actually, let me check this. If you go here, it's in the HTML. So if I visualize that, I should be able to view the numbers. So let me see view data. So what you can see is that you have the values here. So you see recall 0.9, F-score 0.9, precision 0.9. Precision for class 1, 0.8, F-score 0.8, recall 0.8. So both of them, both for class 0 and class 1, values are very close to 1, and you can see them here. But I'm not sure if there is a different way that you can extract them as actual values to be used in a different context. But I hope I can check this out. In the meantime, hopefully, fortunately, this failed. So as you can see, now it's an error. And there are two ways to actually deal with that. So one is to have a look at this information, if it's useful, but also there is a button down here that actually says view or report this error. I'm going to click on that while the other one is running. And I'm going to see this nice table. It actually says that this is execute 1. I have no idea what's going on here. There's a big verb of things here, and if you might require some extra understanding of programming. I cannot claim I do have this level, so I cannot claim that I can understand everything here, but I can go to the last lines and have a look what it says here. And it actually says that class is not found in Axis. In other words, I'm trying to find out class as a label, and it does not exist. And please do something about it, essentially. In other words, I was an idiot, and this is the problem. So what you can do if you cannot figure out what the problem might be, or if it persists, or anything else for that matter, there is a very nice button down here that you can say, okay, I want to report this error if you can help me with that. And you can write a message, your email here, and this is my email, by the way, and you can report on that, and people from the Galaxy team can see it and hopefully address or help out in what the problem might have been in this case. So that was my intention of putting the wrong class in that case. And I'm saying intention now, but a few days ago actually did by accident, and I was trying to figure out what the problem might be. And I think it would be a good enough practice for other people to see what's happening. All right, so this is still running, which is not a good plan. So what I'm going to do, I'm going to go back to my history again, and I'm going to drag also the output of the neighbors. Let me see. This is the result, and I'm also going to drag these 3 files so we can directly see them, and then I can move on to the rest of the other algorithms. So this is the output. Again, if I click on view data, I'm going to be able to see in the output that this is the test data, and if I scroll at the very end, the last column is going to tell me how they've been assigned. And if I go to the confusion matrix now, I'm going to open this in a new tab. It's going to give me again the same, a similar picture. You see that the warm colors are the off diagonal, because in this case you have 0, 0, and 1, 1 here, and the main diagonal numbers are actually quite low. We can go directly to the precision and recall and other parameters to see how or whether they have been improved. And we see now that we have slightly better recall precision in the 0 class, but the 1 class is actually a bit worse off. All in all, however, if we go to the ROC curve, I'm going to open this one now. You see that the ROC curve is actually slightly improved. So the area under the curve is now 0.95. Previously was 0.93. So all in all, our model has been slightly improved. So what I'm going to do now, and I'm going to slightly increase my pace, is I'm going to do the same process with 2 other algorithms. The one is the support vector machines. And again, I'm going to machine learning. And hopefully you see that I'm repeating the steps essentially one after the other. I'm going to select the support vector machines down here. Support vector machines, I've mentioned it during the introduction, but the main concept here is essentially trying to identify what could be a potential I want to avoid using the space as a way to describe that, but what would be a different way to project the features, to change the features, to adapt the features while maintaining the same structure that will help predict the class correctly. So it's a quite interesting method. It's been around for quite some time. And basically, it is using a kernel. Kernel is another word for a different way to transform those features into a different set of features. And depending on the kernel, you identify different classifiers. So in our case, I'm going to go again with to train a model. I have different SVM types. I'm going to like to go for the linear one, which is a fairly, so in other words, the linear in this case stands for what is going to be the kernel we're going to be using. I'm going to select the tabular data as input. The training sample is going again to be the rows. There we go. It does have a header. I'm going to exclude the class with capital C this time. Again, train rows. It does have header, and I'm going to select only the class as the column. So it's exactly the same process as you can see with the ones that we did before. I'm going to click on execute, and it's going to be produce this aspect here. While this is run, and again, hopefully to no big surprise, I'm going to use the exact same process to predict. So instead of doing the training model, I'm going to load the model and predict. The output is going to be the output that's going from job 18 as soon as it's done. 18 in my instance, at least. It's currently running, which is awesome. And in terms of using here the output, I'm going to use the test rows. There we go. Yes, it does contain header, and I'm going to predict the class labels. In all those cases, a good practice is to actually change the name so we can remember what's going on. I assume that this will take some time, so I'm going to click execute here again. So it's going to be put up on the queue. And while it is running, I'm going to my history, and I'm going only to grab the visualization aspects of the SVM. So I'm going straight down here. SVM model result, there we go. This one, and this one, and this one. Going back. There we go. So the model itself is still running, but I can readily now see what the confusion matrix might be. So there is an interesting point here that now we have much warmer color down here. This is a bit, again, in the off direction. And the main diagonal is, I feel, it's a bit more warm than the week before. I can check also the precision recall and F1 scores, and we see that these are really going all over the place. So in the 0 class, we have 0.8, 0.9, and 0.96. So all in all, 0 class is doing fairly okay. However, if we go to the guard class, the recall is quite low, which means that a lot of the instances of class 1 are mislabeled as class 0, which is a problem. Hopefully we will be able to see that also on the rock curve. So I'm going to open this in a new tab as well to be seeing it. And as you can see, the AUC, the area under the curve, has slightly decreased from the previous one. So the SVM model that we produced is slightly worse than the one that we had before. That doesn't necessarily mean that the SVM is not suited for this type of classification problems. What it does mean is that we didn't spend any time actually refining and selecting an appropriate kernel, or even selecting potentially a good set of features to apply the SVM on. The reason I'm mentioning that is that with some interesting cases, I don't want to use the word exceptional because it brings a different notion that I don't want to go down to. There can be used multiple different approaches to a problem with similar outcomes. The question is, what would be the appropriate model that you select based on your problem at hand? So this is the SVM. Final algorithm that I want to run by is the random forest one. So again, I'm going to go to the machine learning down here. Wait. Yes, machine learning. And I'm going to go to ensemble methods. There we go. So random forest, as I mentioned in the introduction as well, is essentially a set of decision trees together, an ensemble of decision trees. In other words, multiple different models combined together in order to produce an outcome. And it's usually trained by identifying which mechanism is going to be used to figure out how to assign a class from multiple different decision trees. And this is sort of the appropriate term here is bugging, but I didn't know where to go to add more complexity to this discussion. So again, I want to train a model. I'm going to select an assembly method. As you can see, there are several different ones here. So what I'm going to select is the random forest classifier directly. We're still using tabular data, nothing has changed. And here I'm going to use as input the train rows again. It does contain headers, and again, I'm going to exclude the class one. The target values is again from the train rows. It does contain headers, and I'm going to select columns again by specifying class. This will allow me to run execute. It's going to be put back on my list. And as soon as this is done, I'm going to apply the same process to do the testing. I'm actually going to do this now to put in the queue, and I'm going to discuss, okay, right now, for me at least, the support network machine has just been completed. So I have the model here, and now it's doing the evaluation of the model with the data here. Oh, and the assembly method is also started, which is pretty awesome. So going back to the assembly methods, now I am training the model, to be honest. Assembly, yes, please. And I'm going to use now to load the model and predict. I'm going to select the assembly method random classifier that is going to put it here. The test I'm going to use is the test rows. It does contain headers, and I want to predict the class labels. I'm going to execute this as well. Because this will probably take time again, I'm going to go to my history, and I'm going to load up the same, there we go, random first, confusion matrix, precision recall, and rock AUC. And going back to my process. So let's check how well the random forests have worked. Let me see first the confusion matrix. All right, so this is much more impressive than the previous ones. We always had red in the 0 class, 0 to 0, but the 1 to 1 was usually in the green area, which means that we always had a few hundred that were not correctly classified. Another important aspect is that I don't know if you've been noticing it, but the confusion matrix always started with a number other than 0. So we had like 100 or 50 here. So now we had actually 0 here and here, which is a good indication. So let's check also the metrics, precision recall and score. And this is quite important, quite interesting. I can try to deactivate those because this is done with Plotly. It's a bit interactive. So I can click on F-score. I can see that F-score is actually 1 in both cases. Recall is 1 in both cases. And regression is also 1 in both cases, which is pretty amazing. And I do expect the ROC curve to be equally impressive. So I'm loading up. And as you can see, this is actually the ideal scenario. You see a sharp increase from 0 to 1, like a vertical one, and then always 1 up until the end. So the AUC is equally 1. This is the best possible scenario. So both evaluation and model creation are still running. So I'm going to, so the question here is, all right, random forest works perfect, right? So what is the advantage? So should we always be using random forest compared to KNN and SVM? Right, so the short answer is that if you go for random forest, if you're talking about overfitting, so really copying, really following the data as they are and not allowing for any relaxed additional data points, you're not going to have a problem there. So overfitting is not going to be a problem with random forest. At the same time, random forest can also be used both in classification and regression tasks. So you can use random forest to do classification, to assign labels, and also to predict values. And Another very commonly used aspect of random forest is to do feature selection. And again, we're going to be discussing this after the demonstration a bit. All right, so random forest has been just complete, I think. Yes, so it's now doing the evaluation in both cases. So by using, so random forest is quite more versatile in that sense. At the same time, support machines can work quite well in non-linear or very complex structured data. So if you have a structure that is non-linear, has some peculiarities, by identifying an appropriate kernel, SVMs might work best. Also, k-nearest neighbors is a fast enough model that you can use to identify what would be the appropriate class. And again, even with k equals to 1, essentially finding your nearest neighbor only, you can usually find some good enough classifiers. Right, and I see that only the evaluation of the FCM still is running, which is good. I have a last point before moving forward. So yes, I should also, it should be remiss of me not to mention that this amazing curve that you saw here, like going direct to 1, is not really the usual, right? So if you find this curve, it's pretty amazing, but it's not easy to find such a well-classified set of data, especially in the real-world scenario. Especially if we're talking about chemical data, which is the systems, it's not always a good approach. Not a good approach, sorry, it's not always the case. Right, so the final approach that we're going to use is to try with a more complex processing pipeline. So we're going to do a value classifier by using the pipeline builder. So for this one, I'm going to go again to the machine learning. There we go. And I'm going to select the pipeline builder right here. So essentially, this is this creates more of a process where we can identify pre-processing steps, estimators, additional steps along the line, and essentially produce a set of classifiers that can be applied for the problem to predict your value. So in our case, we're not going to do any pre-processing. We just want to go directly to the classifier. So the first thing I'm going to do, I'm going to put together an ensemble. So I'm going to create a classifier, and this is going to be using a value classifier. So a lot of models put together and try to find how we can connect them together in order to produce a good result. So it's a value classifier. Our parameters, yes, we want, let me check. All right, so this is ready. So I'm going to execute this and it should run fast enough. So I'm not going to actually create a classifier here. I'm creating a structure for the classifier. And what we need to do afterwards is to find, because as you can see, in this case, I did not put any training data in the process. I only provided the structure that I'm going to use a bagging process of multiple models put together. And I asked Galaxy here to put together the parameters that all those are going to be connected so that I can then provide the training data set for the process to run. So as soon as this is done, I'm going to use the hyperparameter search that you've already seen in order to find. Okay, actually this was done. That was pretty fast. So I'm going to select here data. This is the model. Excellent. So I'm going to change that to our, let's say, final estimator. All right, so I'm going to the hyperparameter search again, and I'm going to specify how we can put together the parameters that fit this bounding model, this final estimator, using our training dataset. So the first thing is to define how Galaxy is going to look through the different parameters. So there are different ways. Exhaustive search is computationally expensive because it's going to go through every value that I'm going to provide. So if you have a large search space and a large number of parameters, this might take a lot of time. So in that case, you might need to go for a randomized search. So I'm going to select the estimator. So this is the pipeline that we just produced. We're not going for deep learning, so I'm going to skip that. And in the search parameter builder, the first thing I'm going to do is I'm going to select, here we go, input data is that. I'm going to select dataset firm. It's going to be, there we go, the parameters that we create for it. So this will contain essentially the table of all the parameters that are going to be used for the badging mechanism. Here, I'm going to identify what are the parameters that are going to be checking against. There are several different options here. What I'm going to select is directly the number of estimators. And the number of estimators is, in other words, how many different models can be used to evaluate the class of the model. So how many different aspects can be used in the classifier. In the search list, I'm going to specify, as you can see here, what are the values that this parameter is going to take. So I'm going to put 5, 10, 20, and 50. A few choices here. I can put range, so you can put like that, or a list, or you can check the help sections here for examples. So this is the parameters, the building the parameters process. Again, it's the dataset of the model. I put the output of the previous one of the pipeline, the final estimator. In the parameters, it's actually the second output of the previous step, which is the set of the parameters that are going to be used, essentially how the weights that these things are going to be connected. Now I need to also provide what is the training data set, right? So I'm going to put what we're talking about tabular data, similar to the previous cases. This is now fairly the same. I'm going to go for the train rows. It does contain headers, and I want to exclude the class. The class labels are again the train rows. It does contain headers, and now I want to select only the class. So the final case, the final questions here are: do we want this process to actually self-test? So in other words, every time it tries to to train the models, should it retain part of the samples, part of the data points to test, or do you have a specific data set? And because we do have a specific data set, I can put nope here. And here, I can select which estimator to save. And in other words, here, I want to save what is the best estimator that's going to be produced. So I'm going to execute that. And again, it's going to be running. And while it is running, I can use this output. As you can see, it produces a number of outputs. We're going to see them as soon as they are done. But also, I can start. I can start with how to to test and to visualize the output. So in order to do that, first I need to test. In this case, if you recall, we did a different approach to previous algorithms, because all the previous ones were specific algorithms. So random forest, this is the one, train the model or test the model. That were the options. In our case, we actually said, okay, we're going to have various models put together, and I want you to figure out what is the best way to connect to each other. Okay, that's done. And as soon as this is done, the output, the final model, is essentially a set of models, an ensemble of models. So in order to evaluate it, test it, I will go to the ensemble methods process. So I'm going to click here, and in the output, in the task, I'm going to go directly to load the model and predict. In the load model, now I'm going to take the output of the pipeline, so the fitted estimator, which is the output we have right now. As testing data, we're going to use the test rows, and because it contains header, we can put yes, and I'm going to ask it to evaluate that. So while this is running, I can test both the parameter sets. So I'm clicking here, and now you can see the output of this process. So in other words, the few iterations, and it tested for 5 estimators, 10 estimators, 20, and 50, exactly the values that I provided in. It is important to note here that it provides a lot of statistics in terms of testing and the scoring and how much time it took, but it also provides the rank. So based on all those aspects, what was the best option? So in this case, the best value that this process found for number of estimators is 20. So although we put 5, 10, 20, 50, the best option was 20, the second best option was 50, the third best option for 10, and the least good option was for 5. And you see here the different testing scores that have produced and so forth. You can also see you can see the weights. You can download this, and it will actually give you a file with that you can load various different stat packages and view it. The final is now we see the output of the testing process, and now you can scroll all the way down here, and you see that now we have the predicted value 1 and 0 for our new classifier. And now that this actually runs successfully, what I'm going to do, I'm going to go back into the confusion matrix and run the confusion matrix from the beginning. There we go. So what's going to be used to test? We're going to use the test rows. The predicted is actually the output of the ensemble process, and the train model is going to be the final estimator. Actually, I want to check that. So this 838 lines, because I might do a 837 lines. All right. 837, 6. Good. Let me run this. All right. So this will produce us the different use pairs, and you can see whether it has been improved or not. So while this is running, let me see if there are any questions that I can address in the meantime, because I think this is sort of the end of what I was planning to discuss.
Maybe before we have a break, there is a couple more questions that Fotis you can address. So how did so this one is about choosing the test and training subsets. So how the training and test data sets are chosen? Why 837 molecules in training and only 218 in the test data sets? And so this is first question. And then the next related to this, can you detail about developing a training and test datasets for unclassified data?
All right, so these are very interesting questions. Let me try to take them point by point. So first of all, a good practice is to have a specific subset of your entire data set left outside completely, so that your model essentially never used them, never sees them. The ratio, it tends to be 1 to 10, 1 to 5, this sort of a range. So in the sense of you have one part used as test and four parts out of the 5 used as train, or 1 part out of 10 as test and 9 parts out of 10 as train. However, a key aspect here is that how you subset your data in order to produce this training and test set is an important decision, in the sense that if it's not fully randomized, or in other words, if the overall distribution of the different classes, if you have multiple labels, for instance, in the 2 different data sets, it's not the same, you might expect significant differences between each other. In other words, you want both your train set and your test set, the distribution of the labels inside them, to closely reflect the reality. So if we're talking about chemical data here, which I have zero information, zero knowledge about, I would like the distribution of the values in the different features, both in the train set and the test set, to correspond to the reality of what these features would happen if I selected any random instance out of the world, right? So this requires some domain expertise in order to ensure that those splits are both correct and representative of the reality. In a lot of cases, people tend to do either manual sampling or like split by selecting the first 9 lines and the 10th line as a test set. It might work, it might also not work. A good process of designing those training and test sets is actually an important part of the training process. If I recall, the second question was, how can you do this if you don't have labels? So if you don't have labels, the question is, what are you training against? So if you don't have labels, you're talking mostly about, you want to do a regression model. So you want to predict an actual value. So it's not really a classification process, it's mostly a regression/prediction process. In this case, again, you want to ensure that the distribution of the values against which you want to model is similar in both cases, and again, representative of the reality. You don't want to have a skew or a bias in these distributions in either data set, because otherwise your model might be trained excellently, but when you start getting new data from completely new data that the model has never seen, either through the test set or from the actual data you want to use for predictions later on, it's not going to work as well as it should be. So I hope I've answered this question somehow. So yeah, yes, please.
No, I just wanted to wrap up the session, but please, Fotis, go ahead.
Right. So because it's also finished the plot, I'm just going to go really fast through this as well. So okay. Sorry, that was not a good AUC, because you can see you actually have now multiple different labels, so this didn't work as good as intended, which means that I did something really wrong in, yes. So this is actually a problem from my side. I selected wrong test and training sets, which means that it tries to do predictions and calculate F-scores for completely different points. which is a problem. I'm very curious to see how the ROC curve looks like. So this is not correct. I'll start by saying that. Okay, this doesn't show at all. Let me actually go back to the history because I'm not sure what I did wrong. And I'm going to pull this one over here. Anyway, so I apologize that I did not end on a high note as I intended. Let me check this one here.
And Fotis, maybe we should do a break now, and then
yes, I'm actually done. So it's an excellent idea. So this is the only thing that I want to highlight. As you can see now, it's not the straight lines as we see before in random forest, for example, but actually the values are very close to 1. It's 0.99, 0.99, 0.99, 98, 97, 98, 99. So it's actually a very good prediction of the classes. So I hope I've been of some assistance in understanding how classification works. The process is very straightforward using Galaxy, and you can use data that is tabularized that most of the tools actually produce in order to create your own classification models. And with that, we can go for a break. And when we come back, I think we have a short talk about feature selection.